Okay, so let's continue. With our analysis, we are talking about that we as designers need to consider the largest value. I remember that in the previous century, okay, in the 20th century, the big problem in ship design, as far as the structure is concerned, was to determine the largest wave that the ship will support in her complete life. That was everybody was just trying to find the largest wave. And with that, we meant that the largest, this wave will produce the largest stresses on the structure. And the problem is that it's not necessarily a very, very, very long wave, because we will see that when we start using MathSurf, that when you consider a very large wave, the result will give you that the ship just goes up and down with the wave and doesn't generate any dynamics. So it's not necessarily the largest in length, okay? Now, if you have a large wave with a high amplitude, yeah, but it's not only that, right? It depends not only on that, but also on the length. So it's a combination of amplitude, length, acting on the ship to generate the largest stress. So in this case, in a very simple way, what we do is we assume that we don't have many of these negative local maxima, okay? If we accept that, so we can take these positive local maxima, prepare a histogram, plot it, and try to generate a regression function for that. And this is this blue. And in these conditions, in this situation, people have found that the Rayleigh probability density function, it's very adequate to resemble these experimental results. And this is the probability density function of the Rayleigh, what we call Rayleigh. One characteristic, as I said before, is that you can integrate this. Okay, so you can get the integral of this. Okay, remember in the case of the normal distribution, you cannot integrate it. So you have to rely on finding the integral, the area, using tables of integration. Okay, people, you are responsible for that because you learned that in the statistics class. And yeah, I'm going to give you a homework on that. So you're forced to remember that. Now, let's talk about how can we use this concept for design. Okay. Let's go on. Let's see if I can move on. Okay. Now, let's suppose that we have this sigma square, okay? With this sigma square, we can define this probability density function. Now, the question is, how can we use this information in order to generate a practical design? Okay, so this is, for example, that we do in instructors, right? Let me see if I can. No, there is no. Okay, so maybe you remember, I'll try to remember for the next session that, and in the introduction of the classification rules, you can read that the rules were developed with the probability of exceedance of 10 to the -8. What do they mean? They mean that, let's suppose that this is not wave elevation, but let's suppose that this is the bending moment. This is the vertical bending moment on the ship, on the midship section. Okay? So what we can do is you can take any value. For example, let's suppose I take this 2, and I take the value of 2 in order to design my ship. Okay, so I take this is my ship, this is midship section, and I apply the bending moment here, a value of 2. What's the problem with this? The problem is that this area here represents the probability that this value of 2 is going to be exceeded. And you can see that this is a very large area. That means that if I take the value of 2 to design my ship, the probability of finding a value of bending moment larger than 2 is very high. That means that after a couple of days or a couple of years, this structure is going to fail. Okay? What can we do? What we can do is we can select another value of the bending moment to design my ship. So I take this value here. So in this case, the value that I take is much larger. But the area here is going to be smaller. That means that if I design my ship with the bending moment of 3, that means that I have to install larger plate, right? Larger stiffeners, because the bending moment is larger. But on my side, I see that the probability to exceed this value is going to be very small. Okay, so in this way, if we define this this curve in blue, we can take a small value for the probability. Okay, and then we go to in this curve and get this value here and take that to design my ship. For example, in the case of the classification rules, they use the probability of exceeding. Okay, so you take the probability that you find a bending moment larger than the value of the design equal to 10 to the minus 8. So this is a very small probability. Okay, so in general, we can consider that if we follow the classification rules, the probability of failing, of having or facing a situation that develops a larger bending moment is going to be very small. Yes, it is correct, but it's not zero. It's not zero because this is a random process. You can always you can expect to find a larger bending moment, but the probability of finding this larger moment is very small. As you can see, 10 to the minus 8 is really very small. Okay, so that's the way we can apply this Rayleigh distribution for the maxima. Okay, so that's why it is so important here. Is there any questions about these people? Any questions about what I just explained? Anybody? Anybody? Okay, let's go on with the. There are other concepts that we can review. This is a very useful, right? Significant value. Let's see if we can find. Mr. Jimenez? Mr. Jimenez, are you there?
Yes, doctor.
Would you please read the definition of the significant value?
The average of the 1/3 of the larger values.
Yeah, that's people. That's the definition of what a significant value is. As Mr. Jimenez said, is the average of the 1/3 of the largest values. Okay, so for example, here we are 17 people. Okay, so 1/3 of this, how much is 1/3 of that, Mr. Zamora? How much is 1/3 of 17? Mr. Zamora? 1/3 of 17? Come on, 17 divided by 3. Come on, Mr. Zamora.
5.7.
Okay, let's go with 6. Okay, let's go with 6. Okay, so in this 6, let's suppose that we choose. Okay, we want to calculate the significant value of the weight of each one of us in this class. What about that? Of the weight. Okay, so we need to choose 6 people who have the largest weight. So I'm going to put here myself. I weigh 180 pounds. We need 6 more people. Ramon, how much do you weigh? Jürgen, Ramon, here. How much do you weigh, Ramon?
100 kilograms.
Nah, so that's, I'm going to put you 195 pounds. I cannot, okay, who else? Mr. Galarza, what's your weight?
Yes, doctor. I have 2,000 pounds.
Oh man, yeah, you're really heavy. Okay, who else? Mr. Iñiguez, what's your weight?
170 pounds.
No, 179. That's Iñiguez. That's 4. We need 2 more. We need 2 more. Who else? Mr. Barba, you're very thin. No, I don't think so. Mr. Delgado. Mr. Delgado. Oh man, you got to. Can you talk, Mr. Delgado? Mr. Delgado, can you talk? You still have problems with your. Okay, let's go on. Mr. Jimenez, how much do you weigh?
175.
There, we need 1 more, the last one. Okay, I'm not going to call any girl in this case because you're gonna hate me. Mr. Zambrano, how much do you weigh?
169.
69? Are you kidding me? No, you're gonna weigh 176. So these 6 are the heaviest persons in this class, okay, which corresponds to 1/3 of the class. And now what we have to do is we have to calculate the average of this. Anybody help me, please? Anybody help me with the average of this? Miss Matias, can you give me the average of this? Miss Matias, can you give me the average of this, please? You need a calculator.
One 184.5.
Okay, so you see, there are 2 steps here. First, you have to determine the 1/3 of the largest. And then you have to go on and calculate the average, right? And that's what we call the significant value of this variable, right? So this is another parameter that we can employ in order to determine or to judge, to evaluate the response of a ship in waves, okay? You will see that in a minute. Now, originally, this parameter was intended to mathematically express the height estimated by a trained observer. Okay, what happened is if you are, let's imagine that you are standing on the deck of a ship and I ask you, see, you're observing the waves. So you try to see, I'm like, okay, I'm asking you, okay, what's the height of this wave? So you try to, not the height, what's the amplitude of the wave? So you try to see the crest, and then there you try to estimate the position of the throw and get the difference. And the difference, of course, is the height of the wave. but it's very difficult because the ship is moving and also the waves are changing its amplitude, right? So it's quite difficult. So what happened was that they observed that and they relate what a trained observer, a person who had a lot of experience, was reporting. And they included something floating. So you can measure physically, you can measure the elevation. And then they compare. And it wasn't the same. So the physical wave height was different than the value that this trained observer was reported. And people found that what the trained reported observer was reporting was simply what later on we call it as the significant value. And it's this, basically he didn't know, but what he did was he reported the average of 1/3 of the largest values, okay? And from that point, yeah, we used quite often, okay? So here, let me erase this because I don't need this anymore. So people, keep this in mind because this is something which is quite common to use in order to evaluate the response of a ship in waves, in regular waves. Okay, so we have something here. This figure, you have it in your class notes, okay? So here, we have the wave height. So let's suppose we have a time register of the wave elevation. So for each one, we break it into increments, intervals, and from each one of these intervals, we measure or determine how often we have this this outcome. And we plot something like this. And here, this is what we call the most probable height. So that's the height, wave height, at which the number of outcomes is the largest. That's that. That's the mean. Okay, so that's the mean value over here. And here is this figure tries to explain you the concept of this significant value. Okay, so let's suppose that here you have a total of n waves. And what we have here is this area, okay, give you 1/3 of the total of this area. And after doing that, as we did in this example, we take the average. So that's the significant height. Okay, and you see here, this is h sub s. Okay, now in some cases, right, it is possible that some people use this another parameter. So instead of having the average of the 1/3, okay, he takes the average of the 1/10. Okay, so this is another parameter that could be employed. This is more common, the significant, but this is also possible to use. Okay, so again, what you have to do is you have to consider how many outcomes, how many results are the 1/10 of the total. And from this 1/10 of the largest, you take the average. So this is another way, another parameter that can be employed in order to evaluate the response. Okay, but let's go back to the significant value. So what we have to do is first determine this value here. So this value here is basically, so this value here, this value here is basically this. Okay, and then we integrate from this value until infinity, and we take the average. The average is z times the probability density function times dz. So since this is the first moment is going to be the average multiplied by the area. But we are saying that this area is 1/3. So here it should be 1/3 here. So if we want this, the average of the 1/3 of the highest, what we do is we take the 1/3 and put it to the right-hand side. And this is the formula that we have. Okay, so remember, we go in 2 steps. First, we determine how many do we need to consider. And then we calculate the average. Okay, for example, in the previous example, we have this histogram for the maxima, right? For the local maxima. Okay, this is the histogram that we had. And then we sum this up. So we have a total of n local maxima divided by 3, okay? And we take the largest. So of course, this is the largest. So if we add these values here, so it's 1, 8, that's 9, 13, 20, 21, 29. So 1/3 of all of this is 29. So we take the largest of this. So we have 8 waves with 2.59, 1 wave with 232 meters, etc. And the last one, we take 1 with height of 123. And then we take all of this and we make the average. And that's the significant value. Okay, that's what we did when we calculated the significant value of the weight of this class. Okay, so that's something that we need to do. Let me ask, have you heard about this concept before, Miss Hidrobo? Have you used the significant value in any class before? Miss
Yeah, I think that in statistics, but I take this signature, this subject a long time ago, so I didn't remember very well.
Okay, good. Miss Vega, did you calculate the significant value of a variable some time ago? Do you remember how to use it? How to calculate it, Miss Vega?
No, doctor, I don't remember.
Oh man, how long ago did you take the statistics class? How long ago? How long ago? Remember? No? Okay, let's move on. The next topic is spectral density. I don't think we're going to have too much time, but at least let's present a couple of at least one slide here. Ms. Lopez, can you read this, please? Ms. Lopez, can you read?
Yeah. The power spectral density (PSD) of the signal describes the power present in the signal as a function of frequency per unit frequency.
Okay, so what we do here is that let's suppose that you have a combination of many waves, regular waves. Okay, each one of these regular waves has a certain length and a certain amplitude, right? So as a result, you have a certain amount of energy, power, as it said here, energy. Okay, but this energy is the result of the contribution of this combination of many harmonic waves, regular waves. Okay, so what we do here is we plot the contribution of each one of these single waves as function of frequency. And that's what we call spectrum. Okay, now it's like having a total energy. But the problem, again, similar to the probability, is that we would like not to depend on the size, okay, the width of the interval. So what we do is we calculate the power or the energy per unit frequency. Okay, so what we do is we take an interval in frequency, a delta omega. Calculate the energy in that range, okay? And then, since this delta omega will affect the result, what we do is we divide this power by the width of the interval. So we get the power per unit frequency, okay? Now, then we take another interval, and of course, for this another interval, the frequency is going to be different. So the result, the spectral density, is going to be different too. So at the end, what we do is we plot versus frequency, we plot this parameter, power spectral density, okay? So when we see a peak in this function, PSD, that means that for that frequency, we can expect a lot of contribution to the total energy or power of the wave elevation. That means that you can expect that in this region of frequency, the wave is going to have a large amplitude. In the other end, if we have a very low power, that means that there is not much amplitude of that wave, okay? So we can identify in this total how much contribute, how much is the contribution from each one of the component, right? Per unit frequency, okay? Now, mathematically, this is the way we calculate it, okay? So this zeta star is the Fourier transform of the wave elevation, of the surface elevation. So you put, for example, something floating, okay, a buoy floating, so you register the elevation up and down, up and down, up and down. That's zeta of time. Then you calculate the Fourier transform. And this here, with this little dash here, up here, that's the complement. So you multiply this times that, I'm sorry, not the complement, the conjugate. You multiply this by that. What do you obtain here? You multiply this complex by this conjugate. Mr. Zamora, what do you obtain with this product? Do you remember? Mr. Zamora, what do you expect? What do you expect when you multiply a complex number times its conjugate? What do you obtain? Do you remember?
The value of the real part.
No, no, no. When you add and divide by 2, yeah, you get the real. In this case, it's the product. Mr. Zambrano, do you remember what do you obtain when you multiply a complex number times its conjugate?
Will be the difference and the square.
Exactly. It's going to be the amplitude square. Yes. So basically, what we're saying here is that you measure the wave elevation or the surface elevation in a certain time. You see that you have to take a very long time because it's saying that you have to take the limit as the time goes to infinity. Of course, we cannot wait that much. So it has to be a very long period of time. You Fourier transform that signal, take the amplitude, right? So you obtain all of this and divide it by the time length. So as you increase time in the denominator, this increasing, but also this number here, it's going to increase. So eventually the quotient will give us a certain limit value. So it's not going to increase because you have an increment in numerator and then also in the denominator. So the quotient will tend to a certain finite value. Okay, so this is the definition of the spectral density. Okay, now if we take the spectral density, okay, we can expect to evaluate the inverse of the inverse Fourier transform of this spectral density. Okay, so this is we just mentioned a few seconds ago the definition of the inverse Fourier transform. Okay, we have to be careful here. Instead of minus is positive. Okay, so let's put this into here, and this is what we obtain. Okay, now this is a Fourier transform which also includes an integration. Okay, so this is a Fourier transform, but remember that this is conjugate. Since zeta is a real function, the conjugate will be, instead of negative, we put positive. Okay, so we have to integrate in time and then integrate in omega. If the function is adequate, I mean, it's continuous, differentiable, that means that we can interchange the integration of the two variables. So in this case, we have to integrate first in time, then in omega. And we're going to interchange that. So instead of that, first we are going to integrate in omega, and then we're going to integrate in time. But here, we integrate the Fourier transform times I omega t plus tau. So this is the inverse. So we have to, we're going to obtain zeta as function of this. So it's not function of t, but t plus tau. Okay, so the result is going to be something that it's possible, probably that you have heard of. Let me see if I can go to the next slide. Okay, there. So this is the inverse Fourier transform, but not a function of t, but t plus tau. But now you are integrating this times that, and you can recall that this is, by definition, the autocorrelation. You are relating the zeta at time t times the zeta at time t plus a certain interval of time, tau. So you try to determine how this value is related to itself, but shifted a certain amount of time, tau. Okay, so what we're saying is that the inverse of the spectral density function is going to be equal to the autocorrelation function. And of course, you can go in the other direction and say that the Fourier transform of the autocorrelation is going to be the spectral density. Okay, so these two relations are what we call the Wiener-Khinchamp relations. Okay, so you go start with the spectral density, get the inverse Fourier transform, and get the autocorrelation. Or if you want, if you have the autocorrelation, you can apply the Fourier transform, and you're going to get the spectral density. Okay, so that's something that we need to have in our mind. And finally, we remember that we can evaluate the autocorrelation at time 0. Okay, so we can say that if tau is 0, okay, tau is 0, this expression, let me go back. Here. Okay, if tau is 0, this will give you 1. So for tau equals 0, this is going to be 1, and you're going to have simply, this is the area under the curve of the spectral density. And you know that this is equal to sigma squared, mean squared, or equal to RMS squared, but only for the case of 0 mean. Now, this is usually our case, right? Because we have, for example, you go up and down, or you go to, you roll, for example, to starboard and also to port with the same rate. That means that the mean value for us is very common, 0. For those cases, this relation holds. The autocorrelation of tau 0 is equal to the area under the spectral density is equal to the mean square. but I have to insist just for this case. Okay, it's 6:30. It's 5:30. I would ask you, is there any questions about these people so far? Any questions about this? I'm going to give you thank you. I'm going to give you an exercise about this, or a homework, short homework about this. So you have to review this material, okay? But now let's see if there are any questions about the report that you have to present. Is there any questions about the report, people? Any questions about the report? No?
Doctor, for my part, I don't have a question because we still doesn't start that.
Okay.
So, yeah.
Okay, I'm just going to review. I'm going to project here. Let's see if I can project something. Okay, can you see the screen, the PDF document?
Yes, doctor.
Okay, so let's just review, make a quick review. So let's try to help you to get started with this work, okay? Let's ask somebody to do some reading. I need a volunteer here to start reading. Anybody wants to start reading?
I could read, doctor.
Okay, go on, please.
Okay, teamwork, objective. Compare the theoretical estimation of the response amplitude operator in role of a simple chip model with those obtained from experimental test.
So that should be quite clear. No? This is what we need to check, okay? And the idea is that with this, after you compare, you can try to determine if let's suppose that the two results, theoretical and experimental, are very close. So what you can say is that all the assumptions that we have done are adequate. If not, what you should do is try to see what do you expect. I mean, what are the good approximation, and try to determine what simplifications are not very useful. Okay, that's the idea behind this procedure. Go on, please. Introduction.
Introduction. Present a short explanation of the importance of roll motion calculation in chip design.
Okay.
Then
Why do you think? Why do you think it is important to calculate this thing? Go on.
Then the various sources of uncertainty to fulfill analytical procedures to calculate the roll response of a chip in waves, damping, wave excitation, nonlinear writing arm relation with roll angle.
So
finally, present the objectives of this report.
Okay, so please, when you write the report, okay, there's going to be an introduction. In this introduction, this is what I expect you to present. Okay, I don't expect to set up here an objective. No. After you explain all of this, you say in a new paragraph, okay, in this project or in this report or whatever, we are going to develop experimental tests, and the objective is this. Okay, so this is part of the introduction. Okay, now here we have the theoretical calculations. You have to calculate the GM. This is something that you already have done. Then you take the free decaying results, right? You apply the logarithmic decrement in order to find the damping coefficient, okay? So you get zeta. Now, since you have the period, this is damped period, right? you can calculate the damped natural frequency. Since you have already zeta, you can calculate the natural frequency. Since you have GM, you have the delta, the displacement, you can calculate the virtual inertia. So you have, there you have a way to check the formulation that you employed in the previous in the previous homework. Okay. Then 3, go on please, response amplitude operator.
Response amplitude operator. Explain the formula to estimate the exciting moment from beam waves and the procedure to calculate the roll amplitude response.
So in this case, it's just to explain. You don't need to deduce it in detail. Why not? Because we did it already at home, in the class. Okay, so just explain how you got it. When we say explain, please concentrate in the simplifications. Okay, so that's something which is very important. Okay, so after you get the results, you can start analyzing and you can say, okay, this simplification is not adequate for the type of tests that we developed, or it is correct or not. Okay, so in this part here, the theoretical roll response, you present the formulations that you're going to apply. The third part, go on, please.
Experimental development. Present a short explanation of how the objectives of the experiment are to be reached.
Please,
describe...
this is not the procedure. This is just how are you going to reach the objectives. Okay. Then go on.
Then describe the equipment employed and the procedure applied to obtain the required information.
Okay, so please see, you can try to see that there is a difference between the first sentence and the second one. The first one is very general, right? It's philosophical. You are expected to try to reach the objective. That's what I want you to tell me first. Then you're going to, after you say, okay, this is the equipment that we're going to use. This is the procedure that we're going to apply. 4, go on.
Discussion of results. After plotting the theoretical and experimental response amplitude operator, comment on the closeness between them.
Okay, so that's something that we need to see. Okay, please, response amplitude operator, remember, is the amplitude of the response divided by the amplitude of the incoming waves. In this case, since we are working with models, I want you to give me degrees in roll per centimeter in incoming waves. Okay, so you calculate that, and also you measure that. You measure the both the or you video record the wave, incoming waves. From this video, you can determine the amplitudes, and also you measure the response. So from the response, you get degrees. From the video, you get centimeters in amplitude of the incoming waves. The quotient of those two are the raw experimentally determined. People, is there any questions about this parameter? Any questions about this parameter? Any questions about this parameter?
Doctor,
No?
I have a question about the raw. Yesterday we consider for 1 centimeter, but in the experimentations we have to measure the length, the
height.
amplitude of the wave.
Yes, yes, yes. Yeah, when you do calculations, yeah, you can specify that the wave amplitude is 1. In the case of the experiment, you set up the shaker. And the motion of a shaker is going to generate waves with a certain amplitude. The problem is that we cannot, well, we could do it, but it's going to be very complicated. So what we do is you simply measure the amplitude of the incoming waves, measure the response, and the quotient between the response and the amplitude of the incoming waves is the RAO. So you have RAO calculated and RAO measured. And then you plot it, and hopefully it will be close. Yes. Did I answer your concern?
Yes, doctor. Thank you.
No problem. Is there any other question, people? No, let's hear from somebody else. Let's hear from a lady. Miss Gutenberg is here. Miss Gutenberg, no. Miss Vega, are you here, Miss Vega?
Yes, doctor.
Could you read the conclusions and recommendations, please?
Conclusion and recommendation. Write the objectives as a research question, and then try to answer it with the result of the experiment.
Okay, so try to think or try to rewrite the objectives as a question. And that's the question that you try to answer with this experiment, right? So when you write the conclusions, basically you are trying to answer the questions that it's equivalent to the objectives, okay? Now, for the recommendations, go on, Ms. Vega.
After answering the research question, describe what other issues.
When you write recommendations, okay, don't write, yeah, you have to be careful with the measurement. No, that's not a recommendation that I expect. That's not a recommendation that I'm expecting from you. Okay? We had, or I proposed a research question. Okay? You have answered that with this experiment. But in this way, okay, when you did this experiment, try to answer this question, new questions have to have arisen. Those are recommendations that I need to see. Takes time? Yes, that's what I want from you. Time. Okay? So don't come to me and saying, yeah, I recommend to be careful taking this measurement. Forget it. That's not a recommendation. I'm not going to accept that. Okay? It takes time? Yes, that's what I want from you. Just sit and do some work. Okay, people? Now, for some reason, I forgot to write here some recommendations about the length. Okay, so you have already a format to write reports, right? The APA, right? People, you have the report from that you employed for the previous report.
Yes, doctor.
Yeah, you have to use the same. Okay, so it's 2 columns and all of that. Now, I'm going to give you 6 pages, no more than that. Okay, including appendixes. Okay, so including appendixes, no more than 6 pages. We don't want to read too much. Okay, if you have any other question, people, please send me an email. I'll try to answer back as soon as I can. Okay. Is there any other question, people? Is there any other question?
No, doctor.
Okay, again, if you need more time, or not more time, if you have any questions about how to calculate this or that, send me an email. I'll try to answer back as soon as I can. Next week, on Tuesday, we're going to have class. Okay. On Monday, I will post a short homework. So you have to do it in 3 days. That's all what we have. Now, on Thursday, we're gonna have an evaluation in person. Okay, 2 p.m. Friday in the morning, we're gonna have lab tests. We're gonna do something similar to what we did in the previous exercise, in the previous lab. But instead of having regular waves, we're going to generate an irregular train of waves. Okay, so the waves going to be like this. So, and the response of the model will be like that. So we're going to register versus time, the roll response. And from there, we're going to see if we can relate the incoming waves spectral density with the response spectral density. Okay, so let's see if we can do something interesting here. Okay, so that's going to be on Friday in the morning. At what time is going to be the test, Mr. Ramon? Mr. Ramon, at what time is going to be the test next week?
In the morning, 8 p.m.
No. The quiz, I'm sorry, the quiz.
2 p.m.
2 p.m. What day?
The Thursday.
Exactly. So where are you right now, Mr. Ramon? Are you in Machala?
No, in Guayaquil.
Okay, so you can be here. Who is outside Guayaquil? Mr. Barba, you are in Guayaquil. You are in Puerto Viejo, right?
Rocafuerte.
Rocafuerte, okay. Miss Vega, you are in La Maná, right?
Yes, sir.
Okay, so you have to travel. Who else? Mr. Carrillo, are you in Riobamba or in Guayaquil?
En Guayaquil today.
Okay, so you're close. Miss Matias, she's in La Peninsula, right? Oh, she's left, she's gone. Miss Astudillo, are you in Machala or in Guayaquil?
I am in Guayaquil, doctor.
Okay, so you're here. Mr. Zamora, you are in Milagro. That's not far away, so it's not so complicated for you. Right?
Yes, doctor.
Okay,
It's fine.
so on Friday, so Thursday, quiz. Friday morning, lab. Friday afternoon, what?
Basketball.
Yes. See you Tuesday. Bye-bye now.